I want to talk about spanning tree and illustrate how is it that spanning tree do what it does and have it then in a visual way illustrated. As we know, spanning tree is a layer 2 protocol that utilizes the spanning tree algorithm to detect redundant links and therefore preventing loops by blocking some of those redundant links. Now, in this hierarchical layer or three-layer topology that I show here, I just want to emphasize that we are going to deal with this topology as if it is a flat layer 2 topology. So we're not implementing any or taking into consideration, like for example, the fact that we can have either channel here or that we can in reality have a layer 3 deployed on the distribution and on the core. But instead, we are going to treat this topology as if it is a flat layer 2 for demonstration purposes. Now, spanning tree. So spanning tree have to go through different stages. The first is that it will select a root bridge, right? So that's the first step. Now, how does it goes about selecting the root bridge? Okay, so well, spanning tree will first look at the priority of every single switch. It does that because when a switch go live, it will immediately send every 2 seconds, it will send a BPDU, right? And inside that BPDU, there is information about the switch itself, including the priority value that it has. Now, how does that priority value is assigned to that switch? Well, it does that by default. And in Cisco switches, every single switch will have the same priority. It can then be changed, and that's what we want to get to in this demonstration. So all switches will have the same priority. Now, if it has the same priority, how can the switches determine which one will be the root bridge? And so eventually every single switch will begin believing that it has the root bridge or that it is the root bridge. But eventually after the BPDU circulate, they all realize that one of them will have a MAC address that is low, therefore it will act as the root bridge. Now, because the priority may be the same with all switches, then spanning tree will use the MAC address of the device to determine which one will be the root bridge. Now, another thing that is important is that it will select the MAC address as the tiebreaker if the priorities are not changed. So if we do not intervene, they're all going to have the same priority, and therefore is going to default to the MAC address to determine the root bridge, which if we know how MAC addresses are assigned, then it is safe to assume that the oldest bridge or the oldest switch in your network most likely will act as the root bridge. And that's not a good thing because, as we know, MAC addresses are assigned to devices at manufacturing, right? Let's say this batch of products will have a set of MAC addresses or a range of MAC addresses that it will keep incrementing as new batches are added to the production. So, in other words, newer bridges will have a higher MAC address. Now, in the spanning tree universe, lower is best, right? Spanning tree will always look for the lowest cost or the lowest value to determine a set of actions. So it will be safe to assume that perhaps if we don't intervene in the spanning tree process, this switch, let's say this switch down here, will be selected as the root bridge. Now that is not a good thing to have because if we have a root bridge that is, let's say, less reliable as these access switches in comparison with the distribution and core switches, these are low-end devices, right, that are not as capable as the devices that we see in the distribution and the core. Therefore, having one of these switches acting as the root will cause problems. What will end up happening is that all traffic will be then passing through that root bridge, and eventually it's going to run out of resources. It's going to become a bottleneck, and eventually it's going to reboot. When it does that, then the entire network will go down. It will take a few minutes before it comes back up, right? But eventually, everything is going to start slowing down to a crawl until eventually it's going to reboot again. That is not a good thing to have. So that's why I want to go through this exercise so you guys can see, visualize the impact of spanning tree and what will happen if we do not intervene. So let's just continue to identify, and let's just, for the sake of demonstration, assign simple numbers to all of these switches as if these switches had this value, right? So 9 and 10. Okay, so let's just assume that these are the bridge IDs, right? So the first step, as I mentioned, was to select the root bridge. Spanning tree has completed that. So next step will be that every single switch will have to have a root port. So that's the first thing. Now, when it comes to determine port status, then spanning tree will take into consideration two factors. First is going to be the cost, and then it's going to be the bridge ID. So if we know that root bridge has been already selected, the next step will be to choose a root port. Every single switch must have a root port. Now, since we said that this down here is the root, right? Let me just try to make that more visible. We're going to now move on to select the root ports. Now, the reward that the root bridge gets for being the root is that all its interfaces will be on the designated port status. Now, let's also complete the list of things that have to happen before spanning tree complete the cycle. So first is the root bridge, then root ports. Yeah, let me just fix that a little bit. And after selecting the root ports, then spanning tree will select the designated port. Then after that, it will block everything else. Okay, so the root port will be the closest to the root bridge, right? Is the path with the lowest cost to reach the root port or the root bridge. So let's take a look at switch number 2. And the cost and the bridge ID will be then the factors that spanning tree will take into consideration in order to assign the ports their different status. Now the cost, what is the cost? What does that mean? Well, every single link has a cost attached to it. So let's say, for example, if we are running a fast Ethernet, right, 100 megabit per second, what we're talking about here is a value or a cost of 19. If we're talking about 1 gig, then we're talking about a value of 4. And if we are dealing with a network that has 10 gigs, then we're talking about a value of 2. So that will be the cost for spanning tree when it comes to taking a look at that fact to make a decision. Now, let's just assume that all this network is about 1 gig, so it has a cost of 4. So every single link has a cost of 4. So if we want to determine the root port for switch 2, then we have two different options. We have this option here going to switch 7, and I have another option going to switch 8. So between those two, we need to then take a look at the cost and the bridge ID. The cost to reach the root port from switch 2 is the same no matter which path it decides to go. If we go through switch 7, it will have a cost of initially 4 going up and another 4 going down. That make a total of 8, and the same thing will happen if we decide to go through switch 8. Okay, so since the cost is a tie, is equal, then the next step the spanning tree we're gonna look at is the bridge ID. The bridge ID in this case, the lowest one, as I mentioned, lower is best, will be 7. So switch 7 will be selected as the path to go through in order to reach the root bridge. Now, this right here will become the root port for switch 2. The same is true for switch 3, 4, 5, and 6 because he had the same exact problem that or situation that switch 2 had. It has two different equal cost paths to reach the root port or the root bridge. So therefore, you're gonna have to default to the bridge ID. So all of this will be the root port for these switches. Now, if we move on to switch 8, switch 7, excuse me, we're gonna have then a is directly attached to the root bridge. So that port right there is going to be the root port. Then for 8, the same thing. For 9, we have again a similar situation that we have on the access layer switch, two equal cost paths to reach the root bridge. So which one is going to take? So it's going to take again the lowest bridge ID. Now we go to switch 10, and the same thing has two different equal cost paths, one through switch 7 and another one through switch 8. Equal cost, you're going to default to the lowest bridge ID, so it's going to choose this as the root port. Now that we have that completed, we move on to the third step, which is every switch must have one designated port or one section between the switch sections. There must be a designated port. Now, what is a section here? Well, a section, when we say a section between switches, we're talking about the links. So this right here is a section. This right here is another section, right? So that is what we're talking about when we say section. So between this section right here, between 9 and 7, we have one root port, so the other one must be designated port. Same thing between a root port and the other end of that section. The other end must be a designated port. Or down here, we have the same situation. Designated port, designated port, designated port, and designated port, designated port. Okay? Now, what about between 9 and 10? We don't have a root port, so but we need a designated port in between those. So how are we gonna go? Again, we're gonna take a look at the cost. So in order to reach the root bridge between 9 and 10, what is the cost? Again, it's the same cost. So since this is the same cost, we're going to choose the bridge ID. And in this case, 9 is going to be lower than 10. Now, between 10 and 8, what will be the one? Well, again, two things. The cost here, 8 has a direct connection to the root, so it is true on both questions. It has a lower cost and also happens to have the lower bridge ID. But since it has a lower cost, we don't even have to take a look at the bridge ID. All right. So now between, let me just fix this a little bit so we don't get confused. Between 9 and 8, and again, it's going to be the same thing. It's going to choose the lowest bridge ID or the lowest cost. All right. So that will be it for the rest of the designated port selection. Now that we have everything covered here, now we move on to the last rule, which is block everything else. So now that we have everything with root ports and designated ports, everything else we have to go and block it. Okay? Block here, block here. All right. And we're gonna block here and here and here and here and here. All right. So that's it. That's all what spanning tree do. Now, in order to help a little bit with what just happened here and illustrate a little bit clearer about what just happened, let me complete that blocking and forwarding illustration. So everything that has a red block X, that link effectively is going to be down. It's going to be blocking. Okay, so we'll be blocking here, we'll be blocking here, we will be blocking here, and we'll be blocking down here, this and this and this and this and this. Now, what end up being forwarding is going to be this right here, this path, this path. Okay, now we can see better the effect of spanning tree. All right, now is that a good thing to have in our topology? It is not a good end result of spanning tree, because we can see right here, right, that we have this root or this switch acting as the root bridge. So everything have to go through this one right here. And as I explained at the beginning, is going to be a bottleneck, not suitable for what we want. Because now if we have people down here, or not people, but critical devices connected, or maybe even a link to the internet, right? Maybe right here, the link to the internet. Well, that's not good, because everybody will have to go through up to the distribution, then down to the root, okay? And then back again up, and then go out to the internet. And that is a horrible, horrible thing to have. So, in order to prevent spanning tree to do something like this, we need to be able to understand, right, what will happen if we don't intervene, and then how we can intervene and change the default settings so we can pick and choose our root bridge as we need it. Okay, so that's uh, for the next video what we'll be trying to do, to manually intervene and change the default settings. So before that, let me just go ahead and pretend that we had done exactly that and that we had chosen a different root bridge, and then show you guys the difference between these two topologies, all right? Or the end result of that spanning tree in the topology. Now, by looking at this topology now, after we have manually changed our default spanning tree uh, values, we have chosen this switch right here on the distribution to be our root bridge, right? So this one right here is our root bridge. And now look at the difference between this selection versus the previous one. In the previous one, we have this dinosaur switch acting as the root bridge, right? And all communication needed to go down here, creating a bottleneck, creating issues to our network. Now we had the root over here in the distribution, and that's what we want. And look, we have an extra link in our high-end devices up here. And also, look what happened. Now, if our critical devices are connected here, then it has a straight route to be distributed within the distribution area or layer, and also to the access layer and the root layer. However, another important thing, your end users will be connected to switches at the access layer. And now all these switches are directly connected to the root bridge. And that is what we want. That is exactly what we wanted. And that is why I have chosen this topology and tried to come up with this illustration. So now we know the importance of being able to intervene in the spanning tree algorithm elections, right? And we need to be able to understand what happens behind the scene. And I hope that this illustration bring that process into light. So we are going to be aware that we need to intervene in order to have a spanning tree that suits our needs. So hope this video was helpful to you, and I see you in the next.